Good afternoon and welcome to Metal Forming Magazine's second annual hot stamping experience, this year presented as a series of educational and informational webinars, but still featuring a plant tour, which will be virtual of course, but you'll get a chance next Tuesday during that plant tour to see hot stamping in action. My name is Brad Kuvan. I'm the editorial director at Metal Forming Magazine and at the Precision Metal Forming Association. And I'm pleased to serve as your moderator today, as well as for part 3 of our webinar series, which will be next Tuesday. So we started the series a couple of days ago, and hopefully you were able to join us for that. But just as a reminder, today's meeting, as well as the others in our hot stamping series, is being recorded for archiving, and all of the recorded archive webinars will be posted to our website after the last event next week. So you'll get an email from us next week that gives you the link to download and review all of the 3 webinars in this series. Also, all of the participants in this meeting are in listen-only mode. So that means that the speaker and other attendees will not be able to hear any audio from your site during the program. However, you can communicate with us throughout the program by submitting any questions or comments using the question box, which is located in the right-hand control panel on your go-to screen. Simply type your question and select Organizer from the drop-down menu. And you'll use that same question panel to ask questions of our speakers at the end of each presentation today. Lastly, before we get started with the presentations, I want to thank our event sponsors, Shea, Fagor, and TJ Snow. Without their support, we would not be able to bring events like this one to you. So much thanks to our sponsors. And to kick things off today, our main event sponsor, Shea, has provided a short video which features some really good video clips of the hot stamping process in action. So we're going to show this 2-minute video, give you a good look at hot stamping, and then we'll be back right after the video to start our technical presentations. Again, thank you to Shea for providing that video, and again to all of our sponsors of this webinar series. So now it's time to begin the webinar. We start with a talk titled Laser Blanking for Delivering Material to Hot Stamping Lines. Our speakers are Matt Mitchell and John Mendia from Fagor. Matt's the National Sales Manager at Fagor Arrasate USA, where he handles sales primarily in the Tier 1, Tier 2 automotive and heavy truck markets throughout throughout the U.S. and Canada. Matt's been with Fagor for 5 years, or for 4 years, I should say, and in the metal stamping industry for 15 years on the capital equipment side with experience in both sales and marketing. And John Mendia has been with Fagor for 8 years, and for the last year, he has served as the firm's product manager for blanking, laser blanking, and cut-to-length lines. So please welcome Matt and John.
Thank you, Brad, for the gracious introduction there. And thank you, everyone, for joining our presentation today on laser blanking lines and benefits and advantages this technology can provide to hot stampers. For today's presentation, John and I will go over the following. John, if you want to go to the next screen, please. Back up one sec. Okay, stay right there. For today's presentation, John and I are going to go over the following. I'm going to go over a brief introduction of Fagor Arrasate, our products, and our U.S. operations. This is mainly for you people that don't know us, and also to validate our expertise on the subject. Then John's going to take over the presentation, and he's going to start with the concept of laser blanking lines, then go on to laser blanking advantages, then move to productivity, cut quality, nesting and stacking flexibility, reductions in time to the market, and future innovations that we're working on with our laser blanking technology for hot stampers. Fagor Arrasate designs, manufactures, and supplies presses, stamping systems, and metal and composite forming solutions. Also coil cutting and processing lines, as well as complete installations to manufacture complex sheet metal parts. That's mainly for the appliance industry, like skins for refrigerators. Fagor is a company that's been in business since 1957 with a stable and profitable growth. We're currently about 850 employees globally. We have 8 manufacturing and assembly facilities. We did about 215 million euros in sales revenue last year. We're a global company, and exports make up about 85% average of our total sales each year. Our portfolio of first-class customers come from both the OEM and tier levels in the automotive industry, as well as from the metal and processing and appliance industry. Some of our main product solutions are high-speed tandem lines, transfer presses with transfer systems, D-stackers, and/or coil feed lines, progressive die presses with feed lines, press hardening or hot stamping lines, both with servomechanical presses, hydraulic presses, and/or servo hydraulic, composite presses with automation, forging presses, tryout presses, cut-to-length lines, slitting lines, press-based blanking lines, laser blanking lines, which we're going to focus on today, stackers, and levelers. All these products and lines can be offered as turnkey solutions, and that's something that we excel in. John, next page. After having sales in the U.S. for a sales office in the U.S. for the last 25 years and a service agreement with Enprotec for the last 6 years, Fagor Arrasate is taking the next steps to be closer than ever to our customers here in the United States and Canada. Despite delays in 2020, which I think everyone can relate to why, we have broken ground on the new facility regardless, and we're moving forward to complete that in May of next year. And you can see the photos up there. The building will be a mix of offices and conference rooms, also spare part storage, as well as a craned working space. This will be a duplicate of our successful after-sales service and support centers that we have established in Mexico and Germany 3 years ago. The staff will be a mix of both expats and domestic natives. Disciplines on our staff are going to be sales, project management, controls programming, service and support coordinators, as well as spare parts. Hiring for the facility has already started. We have about 4 members hired already. One of those is a domestic employee here in the United States, and 3 of them are expats from Fagor, Spain. And at this point, I'm going to turn the presentation over to John, who is going to focus on the technical portion of the presentation, starting with the concept of laser blanking lines. Go ahead, John.
Okay, thank you very much, Matt. So, well, in first place, I would like to introduce a laser blanking line concept for those who are not familiar with it. Basically, it's a blanking line replacing the press by a laser cells and changing the stacker concept to linear robots so that they offer us bigger flexibility. If we go to the inside of the cabinet, we could see that there could be the laser area could be composed by 1 or 3 laser heads, and well, at the end we do have the flexible stacking system. The entry area it's quite similar to a blanking line. Well, in any case, avoiding big pits for the loop and for the press. So now, to understand the line concept more easily, I will show you a video. The entry area, as I said, it's common to cut-to-length lines or blanking lines with coil car and coiler, feeding unit. With a crop shear and the entry for the top of the coil. Leveling afterwards to remove the inner tensions and local effects that the strip may bring. Cassette change, we do it in less than 5 minutes. So focusing in the laser area, any kind of pieces could be cut. Could be a single cutting or combined. Here, as you can see in the image, 2 lasers working together. Part of the scrap can be evacuated directly on the laser area, as you can see now, by opening the space between conveyors. Additionally, cleaning units can be added for skin panels, for example. Well, at the end, we do have linear robot stacking system with a vacuum caps gripper that, as you can see, can be adapted to the different blank shapes. Finally, the pieces can be picked up and oriented in the stacking pallets. Well, at the end, we would have the inspection area and the rejection. So, continuing with the advantages that the laser blanking technology provides the final users. Well, in first point, we would have the most important point that the dies are not required for the cutting operation. So this leads to significant savings. And for example, in automotive industry, every 2-3 years, the car models have a restyling, and every 5 a new model is launched. So this requires new dies, well, every certain time. So, well, the money saved there, it's quite significant. And in another way, the model changing and all these points would the laser cutting makes it easier to modify and go for new models just by changing the cut drawings. As a second advantage, the fast changeovers are really a positive point of this technology, as there's no need to change the dies. And well, just by uploading the cut drawing to the system, the production can start running just by changing the recipe, and no die logistics or any other problems with die logistics do not affect in the process. Additionally, the flexibility that gives us this technology is the capacity to manufacture complex geometry pieces as the die's geometrical constraints disappear. About the materials that can be cut, well, most of them that are required in the automotive industry, and some others that maybe not so conventional in this industry, as copper and brass. One important point is that laser cutting is not conditioned by material strength. Well, that is quite a good point nowadays. So that the material, the car weight lighting tendency leads to more strength materials. So this is a good point, also in favor of laser cutting. About the adaptability that offers this kind of technology is, for example, in a conventional blanking line, if there is a die breakage, the production cannot anymore continue at that point. So the production could be transferred to a blanking line, to any facility where a laser blanking line is installed. Just by uploading the cut drawing, the production could continue. About the production costs, there is also a significant saving. Thanks to the nesting of the blanks, they can be positioned as desired, so saving material. And additionally, edge streaming processes in order to adapt the coil width to the die width is not necessary anymore. So the cost of this extra process is saved as well. Talking about energy consumption, there's a saving as well, comparing with the conventional banking line. And less personnel is required for managing the line, not for let's say operating the line, but just for everything related to die logistics. Talking about maintenance, in maintenance, the savings are quite significant as well, as the maintenance operations are quite simple in the laser cell, and for example, are not necessary qualified personnel for fixing dies like is required in a conventional blanking line. So in maintenance, not high qualified technician would be required. That's one of the key points. And well, additionally, as I said before, with the high strength textiles that are coming out to the market nowadays, well, the dies start wearing faster, so this requires more maintenance. Aluminum, that is also increasing its percentage in the car manufacturing. Well, also has a drawback, that is that the aluminum oxide it's attaching to the knives, and these knives require more cleaning, and also is an extra maintenance operation. And well, finally, as I said, the maintenance time it's lower and less expensive. As you can see here, some example that the consumables of the laser cell are not so expensive. Like some common pieces that are changed are the nozzle, that is like 21 euros each. The ceramic holder, the ceramic nozzle holder is 200 euros each. And the windows to protect the inner lens for the euros, and well, in the aspiration system required for extracting the fumes of the laser cell, 320 euros each. About the installation costs, there's quite big savings as well, as no pits, no high bay buildings, well, reinforced floor for press efforts are required. We estimated that only in foundation over 600,000 euros can be saved. And finally, well, the space that there's a big space saving due to the absence of that as well. We go through the productivities that gives us the laser that can be achieved in the laser technology. With the laser technology, we have divided in 3 different groups. Firstly, we would have the inner parts, pillars, B pillars, and other reinforcement parts that could achieve up to 25 parts per minute throughput. Then there would be some simple blanks like rectangles, omegas, trapezoids. Those ones are quite fast parts, up to 35 parts per minute. And finally, large panels like side panels, up to 10 parts per minute. If we have a closer look to which are the throughput in hot stamping pieces, here we can see some examples of different A and B pillars on different thicknesses, width, and different pitch. So as summing up, as you can see, starting since 10 parts per minute, for the most complex ones, to 28 parts per minute, the simplest one without holes and softer shapes. But as an average, to take an idea, around 17 parts per minute. Well, there's a good point here, because the laser cutting allows us to make some modification in the blank geometries, and these slide geometry modifications may lead to substantial improvements in the throughput. For example, here we have two examples. In the upper part, we have a B pillar that would be cut as in the original cut drawing, and in the lower part, we would assume some deviations in some corners and so on that may not affect to the final part and in the following stamping process. And just by assuming those deviations, the productivity could be increased up to 45% comparing with the original throughput. Oh, sorry, I didn't change the slide. The last explanation was according to this slide. About the cutting quality, by laser cutting, the following tolerances can be achieved. As single cutting, we can achieve up to 0.4 millimeters tolerance. These blanks would be cut by a unique laser head. Then by combined cutting, this means in the same piece, the shape has been cut by by two or more laser heads. And in this case, the tolerance goes up to 0.7 millimeters. 0.7 millimeters. Talking about linearity, the linearity that can be achieved is less than 0.0 millimeters per meter, and the bar is always below 5% and in many cases nearly zero. Additionally, white library is available for different material and thicknesses couples in order to achieve the best cutting conditions and the best cutting quality. Parameters as the standoff, this would be the height, the laser head to the strip, well, the gas pressure, the focal length, and so on. Well, the library for different materials and couples, it's available and optimized for each case. Here we can see an example, two examples of real blanks, and these blanks have been compared with a 3D pattern and measured by a three-dimensional machine. And as you can see in the left part, it would be a single cutting operation, and the deviations below is between minus 0.35 and plus 0.1. And the deviations between holes, those holes used for some of them for guiding in following processes, below between 0.16 and 0.016. On the other hand, if combined cutting would be executed for the same geometry, we can see that the deviation, the tolerance is slightly worse. From minus 0.68 to plus 0.35. And as well, the deviation between holes, the tolerance is slightly bigger as well. What about thinking in cutting parts for tailored blanks? Well, laser cutting, as I said before, the tolerance in linearity is always below than 0.1. That is the minimum, let's say, to guarantee a good welding between pieces. This is as well a real example. And here we do have another real example of tailor welded of a piece for following tailor welded process. So the edge quality, it's also an important matter. In this case, in the laser cutting, the conventional edge shape by mechanical cutting disappears, and this edge it's more straight, more by laser cutting. And here, as you can see as well, this is a real photo from the microscope of a laser cutted blank, and we can barely view any bar in this lower part. So by mechanical cutting with a conventional die, the shearing process, especially with high strength steels, may provoke some edge micro cracks that this could lead afterwards to blank fractures in following stamping process. Well, I'm talking in this case about cold stamping. Additionally, as I said, less bar than in a conventional cutting process is generated, and well, this bar access could also be a problem, because if in the forming process this bar is released, well, it might get adhered to the stamping die and generate some marks, right? And well, this bar as well, plus oiled blanks may cause as well in the following hot stamping process in the stacker. Well, this may lead to some problems in order to de-stack the pieces, because they get attached to another. So, well, the benefits of laser cutting, well, would avoid all these problems, because the bar is nearly zero. And finally, well, talking to aluminum, well, the material in this case adheres more easily to the knives. It's not the aluminum, but the aluminum oxide, and this generates that with the time, well, the edge quality goes deteriorating, and it will lead to a bar increasing. So, and with the time, this will lead to a maintenance operation of knife cleans that well, provokes a production interruption. In order to optimize the cutting quality, there are some systems integrated in the laser head, such as ceramic breakage detection, window dirtiness detection, that, well, tells the operator that, sorry, tells the operator with an alarm, warning, that something something is not correct, and before anything worse happens, would send this alarm. Well, for the cutting quality, the leveling it's also determinant. I mean, because this to guarantee a high quality cutted blanks, because, well, ondulations on the street due to poor leveling force the system, the laser head, to be continuously positioned in the standoff height to this according to these ondulations. So and this has also consequences in the cut edge. Additionally, well, blanks that have been correctly leveled have less internal stresses and better behavior in stamping process. Here I would say for cold stamping. I mean, obviously the leveling is not so critical for hot stamping process. Well, one of the biggest advantages of the laser blanking is the flexibility, and this is achieved with the combination of nesting and the linear robot stacking unit. The nesting software allows the preparation of blank, allows the nesting. I've been talking about the nesting, but the nesting is the positioning of the blanks in the available coil. So as the software lets the technicians to position the blanks as desired in order to reduce the generated scrap to the maximum. But always there is a compromise between productivity and scrap generation. And one positive point is that different references, I mean, 2 different pieces could be cut at the same time by defining a multi-piece nesting. This could be interesting for hot stamping processes, well, where different references are stamped in the same die. Here in the right, you can see an example of well, an original nesting from one side. This would give us a throughput of 30 pieces per minute and a material utilization of 74. But if this nesting is optimized in order to reduce the scrap, as you can see here with another distribution, even the throughput decreases a little bit. Well, there's a quite significant material utilization. I mean, the scrap saving is quite important in this case. This nesting software lets us to divide the different cutting operations between the different laser heads and to make simulations and display them before starting in production. And well, here you can see well what this nesting software could give us. As you can see, in some points there is a shared cut that in a conventional blanking die it's not possible. And you can see how tight the distance between different pieces is in order to save material. This is an example of how easy it is to manage the nesting software. First, is determine the area. I mean, according to the coil specifications. And then we directly upload the drawing and well, position the piece as is desired. This nesting can be done manually, or the software does it also automatically. But by manually doing, the human is capable to see some different configurations that lead to a and to a more optimum solution. About the stacker lets us to position the vacuum cups we saw before in the video in different positions in order to receive the different parts of different shapes, as the examples here in the right. The pieces are picked on the fly, and multiple parts could be taken at the same time and then located in different positions. And as I said before, if in the nesting is set up a multi-piece cutting nesting, let's say, as the one we can see here for that it's a common distribution in hot stamping. Those pieces could be cut so, and afterwards the stacking unit will take the pieces and reorient them in order to position the blanks as it is required for the following hot stamping process. So this would avoid any piles relocating, well, saving time and money, because the same pallet of the blanking could be used for the stacker of the hot stamping process. And this is quite interesting. Here we can see how the pieces could be taken on the fly and oriented afterwards in the pile as wished. As last point, I would like to highlight how the laser technology can help us reducing the time to market in a new model launching process. Well, from one side, the blanking die and design manufacturing are not required. I'm talking about the cut blanking, not the hot stamping die. And well, this leads to shorten the launching process in a couple of months. Additionally, in the industrialization of hot stamping parts, well, it is an iterative process until the optimum is achieved. Let's say it's a test error process where different blank shapes need to be tested in order to see how the material flows in the hot stamping die, and to see which is the most optimum geometry. So in that point, the laser blanking gives us flexibility, and it's very easy to make geometrical changes in order to find that optimum blank. And well, this would also help us in optimizing processes. I mean, during a production during production process, as I said, geometrical changes are really easy to carry out. So, well, in order to find optimization in a forming process, but this is not well, it's not possible, or it's really difficult to do in a conventional blanking, because this would require die modifications, machinings, and so on. But this would be really easy with a laser. Sometimes it would be looking for a better formability, or sometimes maybe not so common, but some, if the following process some errors are detected, or there is a need to execute some changes, these changes are possible, and sometimes could be in order to save material as well, because, well, in a few minutes the CAD drawing can be uploaded, and the line could be running with the new shape without requiring significant stops in the production process. And well, finally, we cannot forget as well that an important fact after hot stamping it's the laser trimming process. that it's actually a bottleneck of this process because it's done piece by piece. So geometrical modifications could be done as well in the laser blanking process, helped by the good tolerances that can be achieved. In some areas that the tolerance is not so critical for further assemblies and so on, well, these areas that require laser trimming could be reduced, saving time and money, of course. Well, and that would be all from my side.
Yeah, thank you, John. Thank you for sharing your knowledge and experience, as well as all the information that you went over. I'm going to give a quick summary on the stuff that we discussed. So I'm just going to give a quick rundown before we do questions. So John first started off on laser blanking concept. So we went over the line, all the aspects of it, and the pieces of equipment that are involved in it. Laser blanking advantages versus traditional blanking. And I'm going to hit some main points on this, and I'm actually going to add some more information as well. Flexibility in material type and usage, blank dimensions, and production needs. I've been talking to hot stampers, and one example that one gave me was the blank dimension adjustability is amazing on this technology, especially the trim line. So going from prototype to PPAP and then ultimately into production, those dies typically have to be adjusted, and it's time consuming and expensive to do that. And with a laser blanking line, you can avoid all that. Scrap reduction, tighter tolerances, no dies required for blanking. No blanking dies are purchased for that, which also increases your competitiveness when bidding for an OEM hot stamp part program. No die degradation, especially as John mentioned, when shearing and punching aluminum. No die maintenance costs, no die changeover time, no die storage for current jobs, no die storage for legacy parts. You just load the coil and enter the old recipe, and you're up and running. So there's no pulling old dies, and you don't have to store them. Increased cut quality. Decreased chance of edge fractures, which is critical on hot stamp parts, since most of them are related to safety. Foundation and building costs. No expensive foundation costs that are related to a press, and no high bay facilities. So you don't have to heat a high bay, as some of you know that as you plant managers look over your costs and you have a high bay area, when you don't need it, you know, your heating costs are a lot higher, as well as, you know, just the structure when doing a new build. And adaptations to disruption production. So if you had two facilities with laser blanking lines, one in Europe and one in Mexico and one in the United States, and you wanted to shift production to your Mexico operation, all you have to do is just send the program. There's no blanking die that you have to send down there. Obviously, you need the hot stamping dies at both facilities, but you have some adaptability by just sending a program. So, and on that note, I want to thank everybody for joining our presentation. I hope you found it interesting and beneficial. If you have any questions, now's the time. Brad, I think, is going to take over here, and then if you want to have a private meeting here in the future, you know, we're willing to do a face-to-face or a virtual meeting, or even a blend of the two. You know, if you're in the United States and you want somebody from the U.S. To visit your facility and see you, but also dial in our experts from Spain, we can do that. So, and on that note, Brad, you want to go ahead and take over?
Excellent. Thanks to Matt and John for the very informative presentation. We'll take just a couple questions now, and then John and Matt have their email addresses up on the screen if you'd like to reach out to them. If we're not able to take your questions right now, I do want to keep us relatively close to schedule, but recognizing that we got a lot of people on the line with a lot of good questions. So, first question for John is talk about the capability of the leveler to produce the flatness required for quality laser cutting. What kind of flatness tolerances can you achieve with the leveler? John, are you there?
Yeah, sorry. I started with when Matt was speaking.
Yeah,
Sorry.
sure.
Yes, depending on the end laser the end leveling quality depends as well on the entry leveling quality. So we are talking that if the leveling quality is less than 50 I units, the exit could be around 4 I units, 5 I units.
Okay, good. Can you talk about the effect of the heat generated by the laser cutting, how it might influence the material, and particularly when that material then goes through the furnace for the hot stamping operation? Does the heat from the laser cutting impact the material?
Yes, by laser cutting there is a, let's say, a small heat affected area, and there are some changes in that small area, but in the thicknesses we are talking about, this affected area, it's around 0.2 or 0.3 millimeters. So actually, it's not a big issue under. It's not this thermal affected area. It's not such a big deal.
Okay, good. So there's a question on ROI. I don't know if you want to get into that, Matt or John. When you compare this technology, or let's say you're replacing a stamping blanking line with this technology, do you want to comment on what type of ROI you see, or do you want to take that offline?
Excuse me, I didn't understand the question.
Yeah, John, return on investment. The investment, how long does it take to typically pay itself off?
You mean the return on the investment?
Yeah, right. Compared to a conventional, blanking line.
Maybe shall we answer that in private? Because
Yeah.
I mean, it depends on the laser blanking configuration. There are 3 laser heads, 2 laser heads, and depending on the kind of products you are running, as the throughput is different, well, this return may change.
Okay, good. All right, so and one last question. On a typical B pillar profile from, let's say, a master coil 1.5 millimeters is the question. What kind of throughput would you expect to get on a line like that?
We could go back.
Yeah, I know you showed some of those numbers, right?
So, here we have different examples. Well, there are some that are bigger. For example, here, if we go to a small one, I know for which vehicle could be this, up to 28. But okay, if we go to a more common, as I said before, an average could be around 17 parts per minute.
Gotcha. Okay, terrific. You want to throw your email addresses back up on the screen for one last second? Sorry we didn't get to every single question, but again, I want to thank Matt and John for that really detailed and interesting presentation. Feel free to reach out to these guys with your additional questions, and we're going to move on. So thanks, guys.
You're welcome. Thank you.
Thank you very much to you.
All right, so our next presentation addresses process parameters and process control specific to the hot stamping process. Our speaker is Dr. Christian Koroschetz. Christian is the Chief Technology Officer at AP&T and a member of the company's executive management team. Christian is responsible for the development of AP&T's products, technologies, and IP portfolio and its respective services. So please welcome Christian.
Thank you, Brett. Thank you for the introduction. Good afternoon to North America and good evening out of Sweden, where I'm currently sitting. It's already dark outside and quite rainy, so I'm happy to be with all of you and welcome everyone to my presentation. As Brett already said, I'm going to talk about process monitoring and control in state-of-the-art press hardening lines. And I will also focus a little bit on components with individualized tailored properties and go also into details when it comes to process monitoring of these type of manufacturing technologies. I will jump directly into the topic. I would like to go into the quality influencing process parameters when talking about direct press hardening as the first part of my presentation. We all know, everyone in this room should, in the meeting, knows about direct press hardening. We have an austenitization phase in a radiation furnace. We have a transfer to the press where we do the forming and the quenching, and then we get a final and hardened part out of the quenching die. So what are the influencing parameters when walking through that press hardening process? First of all, we have the heat treatment process, heating up the material. I brought an example here of a 22 MnB5 with an aluminum silicon coating, 150 grams per square meter in different thicknesses. So what you see in this chart are different blank thicknesses. And what you can clearly see is that every single blank thickness behaves differently when heating the material up. Quite rapidly for low gauges and longer heating time or ramp up time until you reach full austenitization for thicker material. Also good to see if your thermal measuring equipment, thermocouple, is working, because you see those little humps here. The first hump is when the aluminum silicon coating is melting at roughly 600 degrees. It's a change in surface. It's also a parameter that has an influence on the heating curve. And then we have the Curie temperature here at roughly 730 degrees. The next peak or change in the slope in the heating curve. Next on the chart here is a comparison between different coating systems. The chart here shows uncoated material, aluminum silicon coated material, and you have zinc coated material. And you see clearly, depending on which coating you use, you have a different heating characteristic on your material. So you need to know in your press hardening process what type of material you use, because this is heavily influencing your thermal behavior when heating up the material. In the next, we see a comparison between different dwell times and the effect on the interdiffusion layer coating thickness in the final state or before quenching the part in the hot forming die. Main OEMs are requesting a interdiffusion layer of 16 microns. And what I brought here is the dwell times as soon as you have reached 870 degrees. As soon as you have reached that and you add 75 seconds or 600 seconds or 2000 seconds, it has a very large effect on the growth rate and the final thickness of the interdiffusion layer. You can also see that a little bit when you go into press hardening shops and you see parts with different colors. That is an obvious sign for either having the parts, if you had them for a too short time in the furnace, or maybe a too long time, and you see the change of color. So what we typically want to see, the color is also depending on the final temperature that you're using, but what we typically want to see is this bluish color, basically. On the next slide, you can see the influence of the final temperature that you use, that you reach inside the furnace, on the surface roughness, which is of course a requirement for the final paint job that goes on the parts. And you see, depending on the workpiece temperature, surface roughness is changing heavily. And where we want to end up is basically in this window here, between 1.8 and 4 microns in surface roughness. In the next page, we see the influence of different heating times and different final temperatures on the coefficient of friction. And that is very important to understand the influence of the coefficient of friction in the press hardening process, especially when thinking about die wear. High roughness is, of course, leading to adhesive and or more abrasive tool wear. And this is, of course, something we would like to avoid. So you would need to find a temperature time setting, which gives you the best possibilities or results in terms of the coefficient of friction. So we're somewhere here in this area here, where you then can manage to have less abrasive die wear, and you don't need to maintain your dies that often. Then we have the influence when going after the forming. We had the heating process, we had the quenching process, and now we're going into the cooling process. Different sheet thicknesses when transporting the blank during or in air, basically. This is prior to the hot stamping, and then in here we have different quench rates for different thicknesses during the quenching process. So you see, depending on which sheet thickness you're using for the final component, you need to calculate with different cooling rates while transporting the blank in air. The same goes for quenching in a die. Of course, larger thickness or higher thickness has a long or requires a longer quenching time, close die holding time in the tool. Last but not least, the influence of the contact pressure related to the average cooling rate until 200 degrees in kelvins per second or degrees per second here. We have different sheet thicknesses here on this axis, and then we have the different contact pressures that are applied inside the tool, and we have been wearing them from 0.5 megapascal up to 10 megapascal, and what you can immediately see is that the influence is actually not the biggest. So the difference between the different quenching rates is not the highest, and what I want to pinpoint here is that a lot of customers, a lot of stampers out there, we're selling, for example, we're selling press hardening presses from 1200 ton up to 1600 tons, and what we see out on the market that most of the stampers are applying always maximum force, but this is actually not needed. This is causing a lot of energy consumption. It costs a lot of energy, but it's actually not needed because you need to find an optimum. What contact pressure do you need to apply in order to get the best cooling or a sufficient cooling, so to say? So it's a trade-off between cycle time and energy consumption. And then the last slide I brought on the direct press hardening process is, I call it the process window. And I would be happy, this presentation will also be shared afterwards. This is how we set up our lines when delivering them out on the market. Basically, we have a time for the heating, and that is, as we heard before, depending on sheet thickness and surface composition. We heat up the blank to 870 degrees, and we add, as soon as we reach 870 degrees, we add 45 seconds. After these 45 seconds, we have a dwell time window of a minimum 30 seconds. So actually you need to add from 870, you add 75 seconds, and then a maximum of 420 seconds. That is your process window, where you can have the right properties of where you can still reach the right properties in your final coating, which is relation to total coating thickness in the final state, and also the thickness of the interdiffusion layer. And since this presentation will be sent out, I think this should be one of these standards for defining or setting up the heating process in press hardening lines. Next in my presentation, I would like to go in a little bit a newer process. I would like to talk about our temper box and explain the quality influencing parameters when looking into tailored heating. First, what is the temper box? The temper box is a inline heating technology where we can create completely individualized tailored properties. This is, as you can see, not a real component, but it should give an idea what type of hard and soft zones we can create with this type of tailored heating technology. So we can quite conventionally have the soft bottom of a B-pillar, for example, which is nowadays also done by many suppliers and many stampers out there. Can either be done in blank technology, tailored welded blanks to reach different properties in the bottom part for crash behavior. But quite interesting are those localized soft areas that I tried to pinpoint here in certain areas. And this is especially interesting nowadays also for electrified vehicles. In certain areas where when you look at the rollover tests, when you simulate rollover crash, we do need sometimes certain areas with higher ductility. If you would have a crash, that those areas are not too brittle and would not break. So especially in these areas, localized soft zones are quite interesting. But that's only one application. We can also think about soft flanges in the future where we could, and thank you for the nice presentation to Fagor on the 2D blanking, but we also heard something about 3D cutting. So maybe soft flanges can be used to replace 3D laser cutting by conventional trimming in a trim die afterwards, or directly in the press hardening tool. I will go a little bit further into the process. Similar to the direct process we have in austenitization, here in an example of a multi-layer furnace. That's our own product. This is the new product basically, where we combine conventional multi-layer furnace chambers, 5 pieces of them, with a temper box in the bottom of the furnace. You will see some product pictures later on as well. So we have the austenitization. After the austenitization, we transfer the blank into the temper box. And depending on the final mechanical properties that you would like to reach, and depending very much on sheet thickness, we have a time inside the temper box that varies roughly between 30 and 70 seconds. So what we are doing in the temper box is that we keep certain areas that we want to have hard after the quenching process. We keep those areas on temperature in the austenite state, and the other areas we actually cool down close to the transition from cubic bodic center into cubic face centered into the ferrite perlite state, because when quenching this part, certain areas in austenite, certain areas in the ferrite perlite, those areas will be not martensite afterwards, which means they will be soft areas. After the heat treatment process in the temper box, we conventionally transfer the blank into the press, into the forming die, where we have, again, depending on sheet thickness, a quenching time between 5 and 15 seconds. And what you get is a part with quite localized tailored properties, if you wish so. How does the process look like for the temper box? As I said before, we have the austenitization, we have the local cooling, and certain areas we keep on temperature. How do we do that? Inside this temper box, inside this furnace cavity, we have the so-called cooled temper box, which is basically water-cooled masks, where we block certain areas on the blank from the radiation inside this furnace chamber. And what we achieve by blocking these areas from the radiation is you will see that on the next slide, a cooling effect which is similar to cooling the blank on air. This is what I brought you here. We have the austenitization. We mounted on a B-pillar, soft and hard zone. We mounted thermocouples. We measured the temperature increase during the heating. In the next section, we have the transfer out of the conventional austenitization chamber into the temper box. And in the temper box, we ramp up temperatures again in those areas that we would like to harden. There was a slide. I hope everyone can still hear me. I can hear myself twice. No, now it's gone. And the other areas are actually cooled down. And as I said before, similar cooling rates as we would achieve, like we would do cooling on air. And you see this phase transformation here, roughly above, roughly 630 degrees. And close to, before we reach this area where we have the phase transformation, we take the part out of the temper box and transfer the part into the press, into the die, form it and quench it. And you would get those parts with very localized mechanical properties. I also brought you a short video, which I would like to start now. This is a prototype line at a tier 1 in Germany, the company Mendia. We have been heavily working together to to industrialize this temper box technology. What you can see now is the conventional austenitization chamber in our multi-layer furnace, and the furnace feeder fork then transfers the blank into the temper box, where you can already see now the two cooled masks. We drop the blank on pins and move the lower mask towards the upper mask, so that we have the same distance between mask and blank on both sides. We keep it in there, as I said before, depending on sheet thickness, for 30 to 70 seconds, depending on also very much depending on what type of mechanical properties you would like to reach. So thank you very much to the company Mendia here as well for providing us this video. I would also like to now go into further details. One important topic for tailored heating is, of course, the transition zone. And here the temper box provides a neat functionality, because we can actually vary the transition zone. How to do that? I think we should discuss in a more private discussion, but we have possibilities to vary also the transition zone from hard to the soft area. What I wanted to show here is typically technische Lieferantenbedingung from a German OEM who requires a soft zone, which is defined by limits of 170 to 250 Vickers, and the hard zone, which starts at a lower end of 400 Vickers up to 520 Vickers. We have the graph here. We did hardness measurements over the length in different areas of this B-pillar that you also saw in the video. We tested on the flat surface, on the wall area, and in the flange area for different sheet thicknesses. And what you see here, if we have 250, in this case 205 Vickers up to 400 Vickers, we get a transition zone between 25 and 30 millimeters in length. Coming back to process monitoring, an important topic here is the time in temper box and also the temperature levels that you reach after or inside the temper box. What I wanted to show you here is on a 1.8 millimeter thick blank, how the time in the temper box affects actually the final mechanical properties in your soft zone. So if you have the blank too short in your temper box, you will not reach the lower end or the upper end of the soft zone. If you have it too long in the furnace, you basically reach the properties of the soft zone, but maybe you lose in cycle time. So what I wanted to pinpoint here is that it's really important to know the process that you are going to follow and which parameters you should set in your press hardening line. On this slide, I would like to show you the two type of temper box solutions that we have currently on the market. Technology is approved by several OEMs and is already in serial production and is being delivered to, as I said, different OEMs, the final parts, of course. What we see here is the MLF, the combination of the multi-layer furnace for austenitization chambers and a temper box in one tower. Typically, you will also see that in one of the next slides, we would use 4 of these towers in a press hardening line, but we can also add a 2-chamber temper box to, for example, roller hearth furnaces, lines with roller hearth furnaces. Doesn't matter if it's a 90-degree or an L-shaped line or a straight line. And typically, we would also use 2 of these towers so that we have 4 temper box chambers that we can use during the press hardening cycle. In my next slide, I would like to show you what we think is the new standard of press hardening lines. And we are very proud that we already had the possibility to deliver these type of lines. Maybe an information on the side, AP&T is the market leader in press hardening. Why is that? Because we have delivered more than 120 press hardening lines currently on a global basis. And this is what we call the new standard. So this is the state-of-the-art direct press hardening line solutions, including a temper box. This is the line layout, as you can see here. What we have included in this line is, first of all, our latest invention when it comes to the hydraulic press innovation. We have developed a servo hydraulic press which combines 2 worlds. It combines the best out of the hydraulic world and the best of the mechanical world. If you have an interest, especially in the press, I think I will show you my email address later on. You can contact me and we can talk a little bit more about that later on, but that's not the topic for today. And we have in this line, we have, as I said, typically we would use 4 towers of this multi-layer furnace combination with temper box. In total, we have what we call furnace feeders. Those are the feeders that feed the cold material into the furnaces and also the hot material from the austenitization chambers into the temper box and out of that into the either centering table or directly into the press, into the forming die. If we run monolithic parts, and that's the nice thing with this press hardening line, we can run either temper box process or we can run conventional press hardening where you create monolithic parts. If we run monolithic parts for a 0.8 millimeter roof rail and those 4 furnace feeders in total with 20 austenitization cavities, we would reach we do reach a cycle time of 8.5 seconds. A footprint of such a line is 16 by 16 meters, and this is what we have been focusing on from the very beginning since we started to use our own furnace concept, is reduction of floor space, which you can also see on this type of a line that we could also achieve a quite small floor space here. We have, as I said before, we have 4 of these multi-layer furnaces, including the temper box integrated. And if we would go back to a 1.5 millimeter thick material, we are able to reach cycle times of 12 seconds with this type of layout of our latest press hardening line. Now, the second part, why I did all this introduction, is actually the inline process monitoring. Question here is how to monitor quality influencing parameters. So the first part of the presentation was the introduction, what is actually important to watch in the press hardening line. And now I come into the inline process monitoring part. Main objective here is, of course, part quality. To detect process variations and faults, to limit those variations and faults, to also detect die and machine wear, process and product traceability, one important reason for having inline process monitoring, and of course log files to report to OEMs in case they would like to see those specific log files. Then, in addition, we can think about process and line optimization. It's an important part when you would like to optimize the process and the complete production line. Also for energy consumption optimization, it's an important part to have this inline process monitoring in place and the reduction of the scrap rate. What are the most important parameters for the process control? We have here sketched a small tryout line, as we also have it in our headquarters here in Sweden, in Ulricehamn. First parameter we need to monitor is time in furnace. Secondly, the temperature in the furnace. So we all heard these influencing parameters in the first part of my presentation. Now you see that you need to monitor them as well. Then the time in air from furnace to the start of forming needs to be monitored. Temperature prior to and after the forming. Press force, quenching time, the cooling water flow and the cooling water temperature. Hotspot detection after quenching. Those are the most important parameters that I will go a little bit into details later on that we would like to monitor and later on also control in a press hardening line. How do we do that? What type of equipment do we use as our standard? We do use Siemens is our partner for also our automation part of our product portfolio. Siemens PC installed on the floor on a floor standing cabinet. Pyrometers we use from the company Keller. Thermal imaging camera from the company FLIR, and then we have from the company FLIR as well those motorized pan tilt units. The motorized pyrometers with automatic repositioning for temperature detection are based on the front of the press and on the back of the press, where you measure certain spots, certain area, or certain spots on the hot blank when going into the die and before quenching, and then as well after quenching as well. Two cameras actually that we would recommend to install, where we have incoming temperature measurement when coming in with the hot blank, as well after opening the die, where we have hotspot detection. So we measure heat distribution in the blank, which also gives you an idea about your heat treatment process in the furnace, where you can actually detect failures if something is wrong with your heat treatment process. And then more importantly, hotspot detection for checking on die wear, for example, an important parameter to watch. And in addition, we offer cameras for part positioning in the dies to see if parts are possibly misaligned in the die. So what do we recommend as a complete system? We recommend at least one motorized pyrometer, depending very much on how many cavities you run in your dies, but at least one motorized pyrometer and two cameras, two thermal imaging cameras, and of course the process control system. So what we achieve with this recommendation is easy targeting. All the parameters and camera values are set on our HMI, our main control panel. We have a short setting time when introducing new parts. We have an automatic setting during product change. We can look at heat distributions prior to quenching. Goes as well for tailored welded blanks and tailored rolled blanks. The hotspot detection in stereo view after the quenching, after opening the die again, and the optimization of the quench time, depending on how much temperature you have left in the part when opening the die again. And this system is actually fulfilling all the demands for the CQR9 conformity. Also interesting to know. And then the last part of my presentation, after we heard about monitoring. Monitoring is one thing. This is collecting important data. What to do with the data? Yes, you can use the data to control the press hardening process. So next, how to monitor quality influencing, how to control quality influencing parameters, it should say. This is a picture, this is a screenshot of our main panel on the HMI and the human machine interface. This shows actually the monitoring and control of the heating process itself. So what do we see? We can monitor temperatures in the furnace. We can look at dew points. This is what we call the inline process monitoring hot analysis when coming in with a hot blank. The positioning analysis, what I said with the positioning cameras, and then we have the the pyrometer for measuring blank temperature on the hot side. We can also monitor time in air window and coming back to the furnace, soaking time. So this is the monitoring part as well as the control part, because what we can do here is we can set limits, we can set boundaries for certain parameters that we would first of all like to monitor and collect data, but then also use those areas where we set boundaries to control the process. So in case you would go out of those boundaries, you can set certain conditions in the press hardening line, what should be done with those components that are actually out of these boundaries. The next part, we have the quenching process. This is after basically during the quenching process as well as after the quenching process. What we monitor and what we can control and set again those boundaries where we have then certain actions related to those boundaries is the dye cooling water temperature of the cooled dyes, as well as the dye flow, the water flow in the dye, the pressure. We have the dwell time in the tool, press force. And then we have the inline process monitoring part of the cold section. So as soon as we open up, we look at the parts with cameras for hotspot detection, as well as measuring the temperature on the parts by using pyrometers. And again here, possibility to use control by setting those boundaries. What are the limits that are acceptable? What is not acceptable? Last but not least, the temper box process. What we can see here is the same. We need to monitor temperatures, we need to monitor soaking times, we need to monitor time in air, and can set again control values for the temper box process. Before I come to my last slide, what is next at AP&T, I would like to shortly summarize my presentation. You have seen a lot of slides on different parameters that have a large influence on the part quality, and it's a funny story. I have been talking to so many line operators, and I typically go into it's different type of discussions with them. But interesting was once where I asked the operator, "Can you tell me why you heat up the blank?" And he said, "Yeah, to make it better formable." So this should tell you a little bit. We need to still create awareness that press hardening is not an easy process; it's a highly complex process. We need to create awareness that this is actually a heat treatment process, and those OEMs, and it's mainly all OEMs using press hardened components. They are using that for a good reason, to create safety relevant components in their cars. So we as machine suppliers and also the stampers out there, we have a certain responsibility to make sure that we don't get tailored properties into our parts without forcing them into the part, if you know what I mean. So we have a certain responsibility. So what I wanted to show, it's a complex process. We have a lot of parameters that need to be monitored and controlled in order to get high quality parts out of a press hardening line. So what is next at AP&T? We're looking into self-optimizing production lines based on collected machine and process data. Everyone is talking about that, and I'm also talking about it, but this is what we are currently looking into, as well as predictive and plannable maintenance based on collected machine data. You can collect a lot of data, everyone knows that. It's just a matter how you handle this data, how you use it in the best possible way for future production scenarios or future production lines. The picture itself, the slide itself, shows a digital twin. This is what we are heavily working on right now, because we are creating virtual machines that you can, or virtual machines in a virtual factory that can be used for setting and offline operator training. So you can do already offline the setting of a line and the operator training on the digital twin. We also would like to offer our customers then a virtual production and a virtual production planning. It's just a little bit faster than normal press hardening lines, because it's just a matter of computation power that you have in your server infrastructure. And then last but not least, rather large topic is the virtual commissioning of complete production lines based on a digital twin. Quite interesting during the Corona crisis, since most of our customers were not able to have a physical factory acceptance test in our premises. So we actually did first a virtual factory acceptance test, and then we were using Teams and Zoom and video cameras to walk our customers through the actual machines in our plant. But I'm at the end of my presentation, and I would like to thank you for your attention, and I'm happy to receive your questions. Thank you. And last but not least, I need to say, trust is good, but to monitor and to control is actually better.
Very good. Very good. Thank you, Christian. We do have some time for some questions. You did a great job of really explaining how complicated the process is, Christian, but also how the technology is evolving to make the process that much more repeatable and predictable. So we talked a little bit on Tuesday about the impact of die wear on the process, and particularly the contact between the part and the tooling. Are you able to monitor die wear in any way through your process?
Yeah, by having the inline process monitoring cameras where you can actually detect hotspots. So typically hotspots are after opening up the dies and looking at the parts with the thermal imaging cameras. If you see hotspots, this is a typical indication for local die wear.
Okay. The question is, what happens to blanks that leave the furnace for whatever reason at the wrong temperature to go into the press? Are those parts reheat treatable, or do they typically get scrapped?
No, they typically get scrapped. But what you see, we have a quite large window. Yeah, it's actually not that large. We saw in the first part of the presentation a lot. You can influence the surface roughness, the coating thickness. So if you are outside of the window, then you are outside of the window. Scrap the part. Don't reuse them.
Okay. Your multi-layer furnace compared to an inline thermal inline printer, what's the difference in between those two in terms of maintenance requirements, maintenance costs, maintenance activities?
I have not seen a inline printer physically myself. I have seen it from a couple of presentations, of course. But as far as, so I can't speak for the company Schwarz. I can speak for our company. What I know is the temper box is a heating chamber, and you have, as you saw in my presentation, you have cooled masks in there. Basically, the only maintenance is if a heating element breaks or wears out, that you need to exchange the heating element in the heating chamber. But the mask itself doesn't need maintenance because it's cooled. I once opened up the temper box. We had it heated to 930 degrees. and I was touching the mask itself with my bare hand, because you have cooling water going through the mask, and you can actually touch the mask inside a 930-degree environment. And the main advantage of our temper box is that such a mask is actually very easy to machine, because it's out of a relatively soft material. So if you have product changes during your product lifetime, you can machine very easily new masks. It's not really time consuming, a couple of hours to machine new masks, and also very cost efficient, because one set of masks is basically something between $3,000 and $6,000. And that is one of the big advantages that we see with our temper box. I also brought a little bit related to this question, one other slide which compares temper box cost on a typical press iron component with a soft bottom and a hard upper part of the B pillar. If we say the cost for running this part in the temper box is the baseline, if we then compare to tailored tempering in a partially heated tool, the part is 12% more expensive. And then compared on top of it to tailored welded blanks, we have a cost increase of 26%.
Okay, good. Very good. Okay, question is, say I wanted to perform die trimming of PHS. How much of the area softened in the flange? How much is what's the softened zone? How wide is that zone in the flange?
I should have known that this question maybe comes up. I have a slide for that, but I haven't prepared it now. So the colleague that was asking this question, you see my email address. You can write me an email and I can maybe send you the slide. But basically what you need to look into, depending on the CAD design of your model, what you need to make sure is that you have a little bit of soft area and transition zone in your flange, because the transition zone should not move into any radius, and especially not into the wall area, because that has a huge impact on the crash performance then later on. But it's very much depending on the part design. And as I said, you can make a very narrow transition zone, or you can make it wider by setting different parameters in the temper box process. So you are quite free here to adjust that without giving real numbers here.
Okay, good. One last question. We're more or less at the end of our time, but talk about the cost advantage of this technology compared to tailored tempering in the tool, or compared to tailor rolled and tailor welded blanks.
That was this slide.
Okay, good. Okay, good. Well, then, if there's no further questions, yep, good. We'll conclude today's webinar session, which is part 2 of our 3-part webinar series. So I want to thank everyone for attending. Certainly want to thank our presenters and our sponsors as well. We hope everyone found it to be a valuable experience. Once again, an archive recorded version of this program, as well as our previous program on Tuesday, will be available on our website. So that'll be ready next week sometime, and we'll send y'all an email when that is ready with a link to download the presentations and share them with others within your organization. Please join us next Tuesday for part 3 of our webinar series, which includes presentations on laser trimming of hot stamp parts and resistance welding of hot stamp parts, and also features a thorough virtual plant tour of diversified tooling groups, companies, including an up-close look and demonstration of their hot stamping line in production at American Tooling Center. So again, thanks to all, and enjoy the rest of your day. You may close your browsers now, and we'll see you on Tuesday.